All right. We are very happy to have our own David Spivak telling us about menu categories.
Okay, thanks everyone for coming. So for motivation, basically the motivation is that I noticed that lots of people have noticed that poly is cool. And then Valeria noticed that this thing called Dialectica is cool. And whenever someone realizes one of these things is cool, they just start thinking they have to tell everyone because it's so amazing. And then the world's like, okay, all right, maybe. But let me see if I can try to say. So poly is a category, and I came to it because I was interested in how dynamical systems interact, and especially when they can come together and go away from each other. So sometimes they're in an interaction like we are now, and sometimes they're not. And that's kind of how I came to poly. But in fact, that motivation came from motivation from longer ago, which is like, how is it that we kind of make sense of the world, etc. And I originally started with thinking about databases, and I, lo and behold, found databases within poly. So this kind of notion of C-sets and data migration. But the coolness is also in the fact that it has all sorts of monoidal properties. Like it has plus, a coproduct. It has times, a product. It has another operation called tensor, which is really useful for the dynamical systems. And it's got this substitution product, which I denote compose. It's got all limits and co-limits. It's got what are called co-closures for triangle, like what's called a left co-closure and an index left co-closure and a right co-closure, and I'll be talking about those things today. And also, it's got the fact that comonoids, and I'll explain all this, or I'm not going to explain this part, but I'll maybe say a bit of it. If you think of category theory is the study of categories, and categories are exactly the comonoids in poly. So that's just kind of an amazing fact. You're looking in this category, maybe you found it because you like dynamical systems that interact in some weird way, and you find that Amin and Ustalu proved that comonoids in poly are exactly categories. Every category is one of these, and every one of these is a category. And then Steve Audi proved that a universe, like what does he call it? A natural model for dependent type theory. For dependent type theory is a polynomial monad. So we said comonoids or comonads are categories, monads with some property, or monoids for the same operation, this triangle operation, are natural models for dependent type theory. So they're basically for universes. Okay, so this is kind of the motivation. Poly is cool, it's got all these structures, and it's like, why does it have so many cool things? What is all this about? Where are they all coming from? And I just thought, oh well, it's just this amazing thing that God made, and it's really cool. It just does everything. And I don't know anywhere near as much about dialectica categories, and today I'll be talking about dependent dialectica categories, which I think, which I think the name is either due to Tamara von Glen or Sean Moss. But these are ones I understand better, and the reason I understand them better is that both of these are going to come from the same place. A single construction that I'll be talking about that I don't know what to call, so I put it in quotes, and I'll say why I call them this, and hopefully someone can tell me that either there's already a name for these, or that you can think of a better name. Right, so this is kind of the motivation. Where is all this structure coming from? And so now I do know lots about dependent dialectica because I know that it has all the same things that poly has, because I know where they're coming from. Dana, do you have a question?
Why did you call your abstract announcing this talk
agenda and then menu? Well, I was calling it agenda, and then I talked to Josh, and he says, well, agendas are things where you have to do all of them, and I don't see why you have to do all of them. I think it's more like a menu, and I eventually agreed. So now I think they're called menu categories, but later they'll be called something else.
So the agenda changed.
The agenda has changed. Okay, so let me give you the first idea. So here's a proposition. suppose you have a category C. Then the following 5 things are equivalent. Sorry, the following 5 categories are equivalent. 1, the free coproduct, and I'll explain how you get this thing. Oh, actually, I won't. It'll be number 5 is how you get it. The free coproduct completion of C op. 2, the opposite of the free product completion of C. 3, the full subcategory of set to the C, functors from C to set, spanned by coproducts of representables. So you take all the coproducts of representables. A representable is, for every object of C, there's a representable functor from C to set. And you take the full subcategory of functors spanned by the coproducts of those. 4, let U be a universe. So I'm not expecting you to understand this one, so I'm just kind of putting it in quotes. I'll come back to it later. Let U be a universe in the sense of Steve's notion of natural model. Then, and C is a category, then if we take U composed C op is a comonoid, and it'll be a category. So just forget this one. It's sitting there. The point of this talk will be to show that starting with any category, we can do something and find all sorts of operations, and the co-closures and the substitutions will give us many of the symbols here.
And little c there is curly c as a comonoid?
Yeah. So this notion of self-reflective theory is that we're going to be able to define within one of these menu categories or whatever, this sort of work we're going to be doing today, the operations that let you define this very structure that we're talking about. So it's kind of like a kind of fractal inside of itself. And number 5 is the one where you actually get to see what one of these is, what this thing is. So the category, and I'll call it menu C, mn of C, menu category, and y of C. Is that me? Why do I call it that? So the objects with. So what are the objects of this thing? The objects are an object is a pair A, C, where A is a set in our universe. So maybe we fixed our universe U. U is finite sets, or U is whatever. It's a set together with a functor, or a functor from a set is a pretty kind of strange thing to say, but just a set of objects in C. You could say, so what is an object in the menu category? So you have like these set of items, that's A, and for each item, you have some object on the menu, so something you're hoping to receive. So C of A is in ob C. I want to receive this thing. And the reason we're calling it receiving is because of the way morphisms are going to work.
Say again what category A and C are in?
A is in set, and C, little c is a functor from A to C. In other words, A many objects of C.
It's like an index.
It's an indexed bunch of C's. Exactly. Yep. So in the free coproduct co-completion, what is an object there? Well, you pick this set for your index. Maybe I would write one of these things in keeping with number 3 here. I might write this as sum over A and A. There's the index Ted was talking about of like the representable on A. So C of A is an object of C, and so we could write our objects this way. But those are just names. You can this is the actual data of the object, and then HOM from one object AC to another object A prime C prime is going to be a pair F F sharp, where F goes from the indexing set of the first one to the indexing set of the second one. And then for each A in A, F sharp sub A goes from C prime of F of A to C of A. So that's the definition of the menu category. So what's going on? I have this menu full of objects in C. You have this menu full of objects in C prime. What I have to be able to do is for every item I have, I really want to get back this. I really want to get back this C object. But so what I do is I say, hey, would you mind? Or I was thinking of it as an agenda. So I say, from every item I have, I say, hey, I need this from you. And that guy says, I can fulfill that. And they give me some C object. I know how to take their C object and return one of my own. So I get back the C I needed to fulfill. Yeah, Evan?
I was going to say, I think I've seen the free coproduct completion called like FAMC.
Yeah.
So this is like
FAMC op. Yep.
Yeah.
And so you could say, well, why do FAMC op instead of FAMC? FAM is a monad. FAMC op is not a monad. So this is like not quite the same thing. It flips this functor mn, takes a category and returns a new category, but it flips the direction of the op. So it takes what's called cat co to cat. It doesn't flip. It sends a regular category to a regular old category, sends a regular old functor to a regular old functor, but it sends a natural transformation this way to a natural transformation the other way. And this, so it can't be a monad because you can't do it twice, and there's no unit for it and stuff. But what we'll see is that if you do it twice, that thing is a monad.
So that's why we call it a square root.
It's kind of like a square root. We're going to find if we do this twice, we get the free distributive category. Yeah. OK, so what happens if you do this construction to the empty category? If you do this construction to the empty category, then an object of it would be a set together with a functor from that set to the empty category. And if A is not empty, there are no functors from A to the empty category. But if A is empty, then you're OK. So this thing has just one object. Menu category of empty category is 1. And the menu category or free coproduct co-completion of one op is, well, it's a set and then a functor from that set to the one object category. But the one object category is terminal. The morphisms between these things are maps between those sets and then some crazy stuff on the other thing, but who cares because this thing is just terminal. So this thing is set. If we had some U here, it would be the size of the universe. Maybe these are all the countable sets, or maybe these are all the finite sets. But if U is the universe of discourse at all, then this would be set. And then menu of set is poly. It's the free coproduct completion of set op. And so poly is the first time that we have, we'll see that poly is the first time that we have enough structure to define all these operations and in some sense define the very notion itself that we're talking about. This menu category can be defined within poly. It's the first time you could get enough going to do that. But also, what is a menu category of the two object category with one arrow between them? What an object is a set, and for every element of it, either true or false. And then for some reason, you have this set of things, and they're all labeled like true, false, false, whatever. And then you have this other set of things labeled false, true, whatever. And you can send this to which one you want, as long as this is less than that label. Why? I don't really know how to think. Oh, can you fulfill this in the menu? Can the people in back actually make the order? Well, if not, I still might be able to, but if so, then I can too. So if I sent my order to DoorDash, I need to get silverware, napkins, and some Thai food. Well, luckily I have the silverware here. So even though they don't send me the silverware, I still have it or something. But these guys must get sent to false because of the rule that that the thing that I went to has to have a map to the thing that I am. I have to be able to return the thing. So that's kind of a weird category. I don't know what to say about it, but I do know what to say about menu of that thing. Because again, this is just menu of 0 is poly. Menu of the Booleans is dependent dialectica. And again, I don't know if it was Sean Moss or Tamara von Glenn who named this, but I think the work is basically due to those two. And dependent, just like in poly, or in any of these guys, there could be a case where all of the C's were the same object of C and they didn't depend on the A. If you forced me to just pick a single C that didn't depend on A, then that would be a subcategory, and that would be called dialectica here. And over here it would be called lens. So the monomials, people have been talking about lenses a lot lately, and monomials is Valerio de Paiva's original Dialectica. I mean, she has several, but whichever one this is. You'll have to excuse me, I don't remember the name.
So there's like a non-dependent version of menu?
There's a non-dependent version of menu where this C is a fixed object in C,
Right.
and these are forced.
When you talk about monomials, are you converting both of those instances of MN to?
No, I'm sorry, just in the latter. Just in the very last one. Monomials in menus of set equals lens. And monomials in MN of 2. Let's call this thing 2. Say again?
Menu of 2?
Yes.
Is there an interesting story about the objects of menu 2 being predicates or something like that?
Yeah, they're predicates, but why does it go?
Because
Yeah.
right? Okay.
It makes more sense when you do it again because then they go forward. Then you get, so when you do it twice, there exists in X such that for all Y, R of XY, a map from that to, like if that thing entailed that for all, there exists in X prime, for all Y prime, R of X prime, Y prime. This is the story, this is the situation that Valerio was looking at. But I think if you do it once, somehow it's not, I don't know, but it doesn't seem like something gets opposited. It's the coproduct completion of C op, so it's not just exist something. Yeah. So this story is kind of nicer in the is like more motivated that you'd want to do it in this way instead of just jumping right to the second power of this MN thing, because you get to see interesting things along the way. Here, it's hard to say what the first one is meaning, although it very well could be that someone says, oh, this is actually really important. It comes up all the time and blah, blah, blah. I just don't know where. Right, so here's the thing is theorem, I don't know. The free, completely distributive category on C is, if I call it FD of C, that's menu of C. And the free completely distributive category means that it has the objects, so the objects of the free distributive on C. The objects are things like, you have some set that you just write this symbol. It's just a symbol. It will end up being the coproduct, but you can think of it as just a symbol for right now. And for all A and A, B, some B in set of C, A, B. These are the objects. I don't like that. So a choice of A in set, a choice of B in what? Oh, that doesn't make any sense. Sorry. Okay. A in A, B in BA of CAB, where A is in set. There we go. And BA is in set for all A in A, and CAB is in C for all A and B. So these are the objects. This use formal symbols. And you read this, this will end up being the coproduct, this will end up being the product. A map from this thing to another one of these things. If I have one and you have one, I mean, you could just read it off from this definition twice, if you believe this theorem. But B prime, what you do is for each index A and A, you pick one A prime and A prime to go through to, and then for every B prime of that thing, you pick one of these to go to, and then so this went forward, this went backwards, and this one went forward. And that's because we did it twice. Now the C thing is going in the right direction. This sort of thing makes sense.
And that last arrow shouldn't have the thing at the top.
Oh, sorry. Yeah. So this thing is in C, whereas these two are like in set, kind of. It's a function from A to A prime, but really you could per A. Once you fix where your A goes, then you get one of these B primes and you can see where it goes. Yep.
Does this theorem tell us what menu of poly is?
Well, we know what it is. It's this thing, and
Substituting into your theorem for substituting.
Yeah. So menu of C, menu of menu of poly would be menu of set. So it would be the free distributive category on set. Yep. So this free completely distributive category thing, this thing is a monad. So FD taking cat to cat is a monad. In fact, you could form it another way. The free coproduct completion, the free product completion, those are each monads and they distribute. Those are monads that don't flip the direction and they distribute. And so you could say that's the nice way to get FD. But there's two nice ways to get FD. One is nice because it's made out of two monads, and one is nice because you're doing the same thing twice. But I like the one where you do the same thing twice because I'm going to get to carry forward so many things from on every one of the steps. So what this means is if you have a category C, you can send it into the free distributive category on C. What does completely distributive mean? It means if you've got things in the wrong order, of something, then that will be isomorphic to things in the right order. As long as you're willing, these are sets, A and BA are sets. So now we just have to write this kind of, we just have to do this, something terrible, which is to move this pi downstairs. But I mean, it's terrible in the sense that it makes you have to make subscripts that are like that. But we just multiply up all these guys together and have that be the sigma. and then we get to pi over the original thing. And then we have C of A, comma, B of A, because B takes an A and returns something in B of A, and so we can write the same expression again. So completely distributive just means that it's not only distributive that like, this covers the case of like C1 times C2 plus C3 is isomorphic to C1 times C2 plus C1 times C3, and that would be the case that like we have two A's here. A is of size 2, one of these is of size 1, and the other is of size 2, and so that's kind of what we'd get. But this is just saying distributive. Completely distributive means I can index over arbitrary sized things. Okay, so that's what completely distributive means, and that's a monad, meaning that you can take your object C and send it into sigma over 1, pi over 1 of C. And there's also a map from FD of C to FD of C that takes a sigma pi, and kind of like turns that into a pi sigma, turns the middle thing into a sigma pi, and then uses the fact that these are each monads to go one more step. Okay. Questions on any of that?
I think a little silly, but which of these functions are left adjoints? Which are right adjoints? Like how does this affect preservation?
Sorry, I didn't get which functors, FD or menu?
It's free, so I assume everything's a left adjoint.
Menu doesn't even make sense. It's the free coproduct completion of. I don't know. Menu taking cat, co to cat. Is that
Because it's free.
free? Right.
Non-free.
I'm going to have to. It sounds non-silly. It sounds like something that I don't know. I would need to talk to you afterwards. It's a good question. So this one is a left adjoint. But yeah, I don't know. Okay, let's see.
Co, a left adjoint.
Co? God. Okay, so what can I say? Proposition. If C has J-shaped colimits, then the menu category on C has J-shaped limits. So if you have connected limits or connected colimits or coproducts or filtered colimits or whatever, you get that same exact kind of limit in menu C. The other case is not as good, but if C has all limits, then menu of C has all colimits. And this is the sort of thing I just want to do a bunch of right now. Like if C has blah, then menu of C has blah. Something might co, but other than that, it's going to have the same structure. Okay, so here's a fact. Menu is lax monoidal. What does that mean? That means that menu of C times menu of D, the free coproduct completion of C op, the free coproduct completion of D op, multiply those together, and you get a map to the free coproduct completion of C times D op. And that's half of it. And there's a map from the one object category, to menu of 1, which we already know is set. And this takes the unique thing here to the one element set. What does this one do? It takes an object AC. A is the indexer, C is the object being indexed. and an object BD, and it sends it to A times B, and then the thing that sends little, so what, now we index something, and I could have, yeah, we send it to, you probably all know, C of A times D of B.
Comma, right?
Yeah. Okay. So maybe you didn't all know because I'm one of us and I didn't know. But I almost knew. So it's this. So C of A, D of B. Yep. So it's lax monoidal, which means that if I put that the times on the outside moves to the times on the inside. It's a functor from, yeah, let's see. If you have a functor from C to D, C to C prime and D to D prime, you will get a strictly commuting square here. So it's like, it's very reasonable. What this means though, so here's another proposition, and a corollary is that min takes pseudomonoids, and then, but what are pseudomonoids in cat? They're almost monoids. It's just that something's an isomorphism when it should be, when it otherwise would be an equality. Pseudomonoid in cat is a monoidal category. It's not, it would be called a strict monoidal category if this just said monoids. It does take strict monoidal categories to strict monoidal categories, but it also takes all of your favorite monoidal categories to monoidal categories. What that means is that if C has any sort of monoidal structure, then so does menu of C. And so now we just start asking, well, does the empty set have any monoidal structures? No, because monoidal structures need objects. In order to have a monoidal structure, you have to have an object to count as the identity. But 1 has monoidal structures. It has a monoidal structure, has a unique one. 1 has a unique one of every structure. The one object category has a unique monoidal structure, has all limits and co-limits. Maybe those aren't structures, but it has those. It has closures and co-closures. It has everything, and they're all exactly the same. They send 1 to 1. 1 is the terminal topos. Okay, so right. Oh, right. So 1 has a monoidal structure, and therefore set has a monoidal structure. So the unique monoidal structure on 1. So, okay, let me say this again. So that is, i.e., if C with some kind of I and some kind of like monoidal product, I started believing that monoidal products that are not symmetric should have non-symmetric symbols. Is monoidal, then menu C with, I'll just call it I bar, and this thing bar is monoidal too. I'm just naming what you automatically get from this theorem, the proposition. Like you get some structure on menu C. So because the one object category has one of every structure, we're going to get lots of great stuff. But for example, so, oh, I forgot to say this. We also know, I mean, since menu is the coproduct completion, it always has plus. It has like arbitrary coproducts, but in particular, it has binary coproducts. So, So set gets this plus just because it's menu of something. Menu of anything, including menu of 1, gets a plus. But it also gets times. And the reason it gets times is that times is plus, the old plus, overline. and 1 is the old, like, actually, let me say it this way. There is kind of a unique structure. I don't know how to say it. There's kind of a unique thing on 1, and these are coming from that. Is that okay? 1 has a unique monoidal structure, and therefore those lift to menu 1, which is set. But now we have plus and times. And so menu of 1, so this is menu. Menu of set, which is poly. We could do this for Dialectica too. You take any monoidal structure you want on Booleans. So like there's the and or. You're going to get structures on this thing. But anyway, so now we have this fresh plus, because menu of anything has a fresh plus. But it also has this thing, which is old plus overline. And it also has this thing, which is old plus overline, overline, old times overline. There's a lot of symbols on the board there, but what you're seeing is that, I mean, I could also say that we have this fresh 0, we have this old 1 coming from this guy, and we have this new thing called, sometimes like called the identity or whatever we want to call it. I don't know. I sometimes write y. But the point is that the tensor is in fact the oldest operation. It came to us way back from this kind of first place that ever could have any structure at all. It got pushed forward to times on set and then to O times or tensor on poly. And times is the second oldest operation. It came from the fresh plus that existed on set. And plus is the newest operation.
What about the substitution?
Right. So then there's a substitution. So to get there, I think I have time to keep going. So I have to define something else called left multi-adjoint, which is itself a thing you could just learn about. It's due to someone named Dier, 1980 or something. And it's so this just has independent interest. You may find this one day and you didn't know that you had one and you didn't think to call it anything. So so suppose you have a functor from C to D, R, be a functor, it's always left for some reason, a left multi-adjoint. So this is just part of the talk that is just category theory that many people don't know, at least I didn't until very recently. For R is, but I'll phrase it kind of in the terminology of this talk, is a functor Ix from D op to menu of C. So they wouldn't phrase it this way, but now that we have this notation, it's convenient, such that, and an isomorphism. You might say, well, wait, menu C is the opposite of the product completion, so wouldn't it be easier to like take those ops off and use product completion? But it's actually, you'll see that it's, so with natural isomorphism, D maps from C, from D to R of C are in bijection with the sum over all I in I of D. So we apply this thing, and we get like this. Remember how I indexed things? There's like this set here, and that set's right there. And then for every I in it, there's some xi. And so C maps from xi to C. So I was able to move this R off as though it was a left adjoint. But the cost was I needed to add up a bunch of Hom sets. So any right adjoint, any left, if R is actually a right adjoint, then it has a left adjoint. It has a left multi-adjoint too. But this is much more common. So, so for example, every parametric right adjoint is one of these. But you can forget that unless that's interesting to you. Yes?
They call it multi-adjoint because it has to be described as a sum.
Yeah, it has to be. It's called a multi-adjoint because it has to be described as a sum. Yeah. So then I want to go on and say a monoidal product, this shape, has this is a new definition here, has a left or a right index co-closure. Okay, that's kind of terrible. I maybe should call it multi-co-closure or something, but so left means that like for all C in ob C, C, this thing blank, has a left multi-adjoint. And this one says blank triangle C has a left multi-adjoint. Okay, so I have about 10 minutes left. So let me give you some examples. If C has products, if C has products, then C maps from C1 to C1 times C2 is the same thing as C maps from is the same thing as sum over maps from C to C1 of C maps from C to C2. And so times would have both a left and a right index co-closure. So if you have products, then product is a index co-closure, or it has an index co-closure. So this is quite common. You don't need something special, just products. If C is extensive, that means it has nice coproducts and has a terminal object. Then maps from C to C1 plus C2 are in bijection with the sum over all F's from C to C1 plus 1 of C maps from the inverse image of 1 to C2. So if you want to map from C into C1 plus C2, you could say, well, let me just give you a map from C to C1 plus 1 to maybe C1, and then take the stuff that went into the bad part and just map that into C2. And so plus has an index co-closure a lot of times. So this is like pretty common, this index co-closure. And now there's just a bunch of stuff we can say. And I'm not going to be able to say all of it, but basically, like if C is monoidal closed, then menu C is index co-closed. I probably should. So if you have some operation, then that operation over line is index co-closed. So it's monoidal closed on the left, then it's an index co-closed on the left, and it's monoidal closed on the right, then it's index co-closed on the right. If C is index co-closed for some monoidal operation, then C bar, menu C, is co-closed, closed, monoidal closed. But now getting to Wesley's question, I probably could have gotten to this earlier. For any monoidal category, oh, and so the point is, if we're just going to build stuff up one piece at a time, one has every possible structure, and therefore it's monoidal closed, it's index co-closed, so therefore the next one is both, and then therefore the next one is both, et cetera. Yeah, so we get to kind of keep what we had. It just kind of often goes. For any monoidal category, C, I, this thing, free distributive on C, which is, again, the menu of the menu. I have a menu of menus, C, has a substitution product. this last thing. So I'll call it, okay, what is that thing? So what it does is it takes, what you do is you have like some sigma over A of pi over B of C, and you want to compose it with, using your old structure on the inside, but this new thing on the outside, with sigma over A prime of pi over B prime of C prime. And what you get is, it's not so bad because everything's free. So what you get is the sum over A of the product over B of the sum over A prime of the product over B prime of C A B. Maybe I should have written that. A B, A prime, B prime. Old one on the inside, C prime, A prime, B prime. And so you get to carry your old thing forward. And so we found all of these in poly. We've also found them all in dial. We found 2 of them in dial, one for and, one for or. And is a monoidal product. And if C is left or right index co-closed with its like this thing, then free distributive or menu of C is with its thing is the same. Actually, one of them gets a little better. I think right goes from index co-closed all the way to co-closed. You get to, for some reason, get rid of the multi. For some reason, is also. And I forgot to write this, but I think it'll be the last thing I say. FDC from P, from some object to Q composed R. I denote the co-closure, the right co-closure with this strange, well, this kind of bracket symbol here. And so what this means is that we've now defined this operation in this general case. Whenever we have menu of something. We've also defined this symbol in this general case. And when we do this for the case of the unique monoidal structure on 1, we get to write things like, we have a universe, say. Well, that's maybe a little rude because I don't know what that is. Maybe I didn't tell you what a universe is, and maybe I don't even know how. So maybe this isn't quite good. But in fact, this is, no, actually I could say it for anything. For any P, for any polynomial, or object of menu C. If C is a comonad, then this thing is again, oh, I know, sorry. Okay, now I'm going to insert one more thing. I'm not really quite done. Nelson and his group in the MRC, Nelson New, and the MRC group that I don't know all the names of, showed, or haven't written up yet, but they showed that comonads in the free distributive category on C are categories enriched in menu C. So I knew that, and Amanouslou showed that comonads in poly are categories. They should have said categories enriched in set, because it's always categories enriched in the previous one. So comonads, comonoids for this thing are categories enriched in menu of menu C. And so this thing will always be a comonoid, and therefore will always be a category enriched in menu C. And so there's almost enough to write this little, I just don't know what that op is. There's like all the symbols are there to define the entire structure we're talking about. Like this thing, if you remember, was menu of C. Remember that was the fourth one that I put in parentheses? So we almost have enough to just specify ourselves right inside of ourselves. But I'm missing that op. So, but that's what I'd love to understand that op. And if anyone has any ideas about that op, please let me know. And that's it. So thanks.
Have you had a chance to put some of this in your book draft yet?
No, we haven't. And that's the problem with that book is the stuff is moving so quickly that, no, we haven't put it in the book. I don't know if we will put it in the book.
Well, it's God-given.
It's got, well, it is. The book is more geared towards dynamical systems and applications from that point of view, rather than theory. But it's got a lot of theory in it, so maybe we'll try. Other questions? Yeah.
Are there some other categories besides like 1 and 2 that are interesting to start with?
If you do set op, menu of set op, you get the Dirichlet polynomials, which are like bundles. I don't know any other ones. Oh, sorry. Yes, I know tons of them. So, so FD of if you have some. So Paolo Perrone gave a talk called about weighted categories in our colloquium, and FD of, let's say FD of the monoid of real numbers equals like R weighted categories. So what is one? An R weighted category is a category. Sorry, let me say, what is a category enriched in menu C? It's a category where you've got objects, but there's a set, like what is the Hom set between two objects C1 and C2? The Hom set between C1 and C2 is a Hom object. It's an object in menu C. So it consists of a pair consisting of a set, and then for every element of that set, an object in C. So you actually get to say, I have a set of morphisms from C1 to C2, and each one is labeled by some object in R, or whatever this category here is. And the rule is that if you have 2, what does it mean to be enriched? It means that that because it goes backwards, it says, because menu C is kind of opt, it says that this number must be, that's too much of a shortcut. Okay, that number must be less than or equal to the sum of those two numbers. Oops, I forgot to say this was less than with plus, the monoidal category. So a weighted category is one where you, every morphism is labeled by some weight, and that this weight has to be, I mean, in Paolo's talk, I think he had this being greater than or equal to this, because for Levier metric spaces, for example, they often think of it this way. But menu C wants the error to go that way. So yeah, so right. Yeah.
Oh, no, I was just going to say, did I understand you? So the weights now are going to be members of the menu.
Of what?
There'll be objects in the menu.
No, sorry. The Hom sets will be a Hom menu. There's a whole Hom menu between C1 and C2. What that means is there's a set of maps from C1 to C2, but everyone is labeled by a single object in C. There's no more menuing to go.
I see.
Yeah. So this is just like a number, or you could. It's a family of them, and you just draw each one of them as an arrow, but with a weighting on it, a weight. Bah! Sorry. Thank you, Brendan. Co-monoids in this. Oof, they're terrible. Thank you. Co-monoids in that. I forget your question, Evan. Did I still answer it, even though okay. Yeah.
And that works for any monoid.
Oh, this works for any category here. Yep, you put any category, and you're supposed to label your morphisms with objects in that category. You're supposed to give a map that way.
Right, because these are categories enriched in weighted sets.
Yes.
If you're using this to resolve
Yeah. Nelson's result says that categories, comonoids in poly are categories enriched in weighted 1. And weighted, so in menu 1, which is categories in weighted set. Yeah, so those are set weighted. What? Every morphism is labeled by a 1, by an object of 1. Okay, yeah, that was a little convoluted, but yeah.
You said that when you are working with 1 to get poly, you get lots of structures that you get for free on 1 that get pushed through?
Yeah. So 1 is like, yeah, I'll just repeat the question. Yeah, 1 has tons of structures that get pushed forward through to poly, and the point is why. 1 is monoidal closed, 1 is index co-closed, left, right, blah, blah, blah.
Does
Yeah.
a similar thing happen for 2?
Yeah, so 2 has all sorts of monoidal structures. Well, it has 2 monoidal structures, I think, and an or. Each and is closed. It's got implies. I don't know if or is index co-closed because it's a coproduct. And coproducts, oh, is it extensive? It's probably extensive, but if it's not, then the following is false. So it has, it's co-closed, index co-closed, but with the or. So you can just kind of like trace them all forward. Maybe you get a bunch of stuff. Yeah. And so the point is none of this is like random. All of it, well, maybe this one. I don't know about that one. I think I added that later, and I'm not sure. But all of this stuff is not random. It's just stuff you get for free because it always will be there.